Hello and welcome. Today we're discussing section 7.5, Constrained Optimization, the method of Lagrange multipliers. In this first video, we're going to predictably tackle this first learning objective, just to study this method as a method for finding points where an optimized value might be found subject to some kind of constraint. And we need to talk about what any of those words might mean. So what this method says basically is you want to find the largest value of some function, but your values of x and y are restricted in some fashion. So the broadest kind of examples from 7.3, where we also did maximize, minimize kind of stuff, were that we generally didn't have a constraint for our x's and y's, or if we did, they were inequalities. We had a whole region on which to work. Here we're actually narrowing ourselves down to an equation that restricts what our x's and y's can do. So the method that pertains to this says basically, predictably, given what else we've been up to in this chapter, we find partial derivatives of all these things. So first partials of the function we want to maximize, the partials of this so-called constraint equation, and then basically the claim is, and there's a geometric argument for this, that what we want is for the partials of the function we're interested in to be proportional to the partials of the constraint equation. And so the visual argument is basically that we want the level curves of f to rise just to the point where it touches this constraint, because we know we have to operate on this constraint formula. And so what happens there is that the point of tangency between these two graphs gives us the ratio of these derivatives need to be proportional to one another. That's got to happen in both directions. And then we've also got to actually fall onto this constraint equation. So we end up with basically three equations. We need to all be true. And the extra little piece of excitement thrown in there is that we have this constant of proportionality, which is usually called the Lagrange multiplier. This is the Greek letter lambda, by the way. Okay, so we solve this equation, we find whatever points we come up with, and then the largest value of that is the largest. If we're trying to maximize this function or minimize it, then the largest among those lists of relative extrema would find the one we're looking for. So, like most things, it doesn't really make sense from a theorem, and it makes potentially more sense once we actually try an example out. So we'll do one without any context. We'll do one with just the bare math problem and see if we can't figure out at least the basics here. So we're trying to find a maximum value for this function. And if you're sort of in the 7.3 mindset, that might make you think, this must be where we take the first partials and set them equal to 0 and yada, yada, yada. But unfortunately, because there's this follow-up sentence, or the rest of that sentence that says that there's a constraint here, these two things put together, trying to maximize something with some constraint on it, so maximum value, but with a restriction on the x and y values, this is sort of what leads us into 7.5 territory. Conceptually, what we're dealing with is that if we imagine the 7.3 question is, we have some meadow with some rolling hills in it, and if we're wandering around out in this area and we get to go wherever we want, we could look for the place that has the highest hill in the whole land. That would be the global maximum, and the strategies of 7.3 would help us out with that too. So 7.5 is basically saying, instead of us getting to wander around in this meadow willy-nilly, there's some specific path that we're restricted to. So we're on some road or other path that kind of says, sure, you can see these other things, but we're only allowed to walk along this path. And there should, in general, often be still an answer to where is the largest spot along that path. Where would the biggest little bump on this road be, even if it's compared to some other hill that's off to the side, off of the path, not the largest spot. So it's a relative extremum, but on this path. Okay, so our strategy says we're going to take first partials, which is sort of what we've been up to. And just as a reminder, our f function looks something like xy squared, and then minus x squared y. And so what we're looking at is first partials. We have to make sure that we know what we're up to here. It's easy to mess these up with the whole taking partial derivatives and leaving this other variable constant. So y squared is constant for this purpose. So x is going to have a derivative of 1. It's going to leave us with y squared. Derivative of the second term is going to be 2x, and the y is going to get left alone. Similarly, for this y partial derivative, we're taking the derivative with respect to y, so the 2 is going to come down, x is going to get left alone. And then this second term, the y is going to be, its derivative is going to be 1, so we'll end up with just x squared. The claim from this strategy is we're going to take these first partials and set them equal to the partial derivatives of the constraint equation. So we're going to take this one here and say, okay, here is our g sub x. And remember, the derivative, our constraint equation by itself looked like x minus y equals 10. So the derivative of this with respect to x is just 1. The derivative of that same left side, just the variable components, g sub y, would be negative 1. So there's our other half. And we're setting this equation up so that these two things could be equal to one another. Now, there's a bunch of different strategies that we could employ at this point, and I want to acknowledge that this is opening up to a variety of options. The one that I'm going to try to employ here is to solve both of these equations for lambda, and then use them in our constraint equation, this third piece, to come up with an actual value for x and y. So the best hope usually from these first two equations is that we get some relationship between our x and y things together, and that allows us to say, okay, well, y in terms of x, and then we can plug that into this last equation and make it all work. So we solve each of these things for lambda. Notice that all we had to do in the second equation was multiply by negative 1. So the signs of both of those terms changed from the previous slide. And then setting these things equal to one another, the advantage being both of these things are equal to lambda. So if they're both equal to lambda, they're both equal to each other too. And then lastly, we can say, look, we've got this same term on both sides. That negative 2xy can go away, so we're just looking at y squared equal to x squared. So we have to be a little bit careful with the positives and negatives here and whatnot, but the ultimate result of this is that plus or minus x is equal to plus or minus y. Another way of expressing that is in absolute values like this. And so including that constraint equation where y is the same thing as 10 minus x, we get basically that x is either 5, x is 5 and y is either plus or minus 5. So these two things, these give us 2 points together, either 5 comma 5 or 5 comma negative 5 for our inputs. And since we were looking for a single maximum, we're going to have to actually do some comparison. So our 2 points that we input were these guys right here, 5 negative 5 and 5 positive 5. So we're going to compare the outputs in our original function. So we're going all the way back to plain old f. Plugging in 5 for all the x's, negative 5 for all the y's. We get 250 from the first one. Plugging in 5 for both x and y, actually a bunch of stuff cancels out, and we get 0. So what that all amounts to is the maximum value is 250, and that's what we're being asked to put together. So that's it for this video. We'll leave that word problem for our next one.